Hello and welcome to the NISER lecture series on quantum chemistry by Dr. Arindam Ghosh of School of Chemical Sciences, NISER. So we will continue our discussion on simple linear harmonic oscillator, and this is lecture 2 of that series. Before going to the lecture 2, let us quickly summarize what we have done in lecture 1. Let me write down the key steps of the theory that we have discussed so far, we have formulated so far. So we got the primary equation for the space part of the simple harmonic oscillator is given by this equation where we defined certain symbols, like for example m is the mass of the particle, omega is the frequency of oscillation, etc. And then we did certain substitutions. For example, we defined alpha to be a fraction m omega over h cross, beta is equal to 2me over h cross square, epsilon, which we found out that is going to be a dimensionless number if we define it to be beta over alpha. And finally, we changed the variable from x to q, and q and x are related in this way. So if we use these substitutions and the change of variable, then we get the transformed equation this way. And the first attempt to solve this equation, what we did is that we tried to find the asymptotic part first, the asymptotic solution first, which is the behavior of the solution when Q is large, Q tends to plus or minus infinity. And we found out that the form of this asymptotic solution, something like A, some amplitude A, an exponential minus q square over 2, fits well to this equation. We checked that in lecture 1, and then we confirmed that this is going to be our asymptotic part. And then as next step, we try to find the total solution, which is the psi of q. We retain the asymptotic part, but then we inserted a function of q, the f, and that particular function will determine how the solution will behave when q is not so large. When q is large, then the asymptotic part will take over f, and then the total solution is going to be complete when we'll come to know what this f is all about. The next step that we did is that we inserted this psi in this equation, and then we found a new equation involving f, which is given by this equation. And then the next step that we did, well, this equation is not complete. Let me complete it. So this should be a 0 over here. But now this equation is complete. So as a next step, what we try to do is that we have to solve this equation, and we try to use the series solution method for this. We assumed f to be an infinite series of this form. This is an infinite power series. And when we plugged in this form into this equation, we found the recurrence relation involving a particular coefficient ai with another coefficient ai plus 2 in this manner. And there, and exactly here, we stopped lecture 1 and will be continuing from here in lecture 2. So we have got this solution for f in the form of an infinite power series where these coefficients are given by this recurrence relation, and this f is going to constitute the total solution for the linear harmonic oscillator along with the asymptotic part. But we should first now check whether this particular series solution that we have just obtained, whether this is a good solution or not. By good solution, I mean whether this solution is acceptable by quantum mechanics or not. Because ultimately, when this F along with the asymptotic part will constitute the total solution, the psi of x or psi of q, this psi of q should, in principle, never goes to infinity as q goes to plus or minus infinity, because that is the whole purpose. We brought the asymptotic part and then we gave the asymptotic part just to ensure that this wave function should go to zero slowly, smoothly, as q goes to plus or minus infinity. But now we have to include this f over here, and this f is basically is going to be an infinite power series of this particular form, where this a, I are given by this recurrence relationship over here, correct? Now, this whole thing, we need to first check whether this combination of the f and the asymptotic part together, whether we have the psi to be an acceptable solution or not. Now, the question is that how to check that. For checking that, what we need to do is that we have to check how this recurrence relation gives us the behavior of two consecutive coefficients when I is very large. What do you mean by I is very large is that after all, this is an infinite series, and in any infinite series, when we have actually a very large number of terms, then that particular series corresponded to this particular function, right? So for checking how a particular series is behaving, what is the functional behavior of a particular series, we need to check how the coefficients are behaving when this index is very large. Let me give a simple example of what I'm talking about before actually checking how f behaves. So let us talk about the sine function. We all know that the sine x can be expanded in an infinite power series. It's called the Taylor expansion of sine x, and it is given in this particular form. Is x minus x cubed over factorial 3 plus x to the power 5 over factorial 5, and so on and so forth. And now if we try to draw this sine x, we know that it's going to be something like this. So you have the sine function going up and down. It is definitely not up to the scale. I'm going a bit too much on top and a little too less in the bottom. Please excuse me for that. But nonetheless, sine x is an oscillatory function like this. But now, if we ignore higher terms and if we just look at the very first term in this particular series, this function, if we try to plot it, this function is not oscillatory at all, but rather this function is something like this. It is definitely an odd function, like the sine x is an odd function. In fact, each of them are odd functions. An odd function can never be represented by an even function on the right hand side. That's acceptable. But what I'm trying to say is that if we simply truncate this series at the very first term, this series will no more represent this function. So in order to this series to represent this function, we need to keep several terms. So let's see another picture that I have downloaded from Wikipedia, that where we have we have plotted not only the first one but first few, and let's see how does that look like. So now we have this picture where many of the terms are being drawn. So I have already tried drawing the first one, as the x, which is also the order 1, which is also this red line, this x. And then we have the 3 x cubed over here. Then we have x to the power 5 over here, this yellow line. Then we have x to the power 7, that is this green line, x to the power 9, this is blue, x to the power 11, this is black, and then x to the power 13, this is this pink line. So what is coming out is that when we are going higher and higher powers, then it has started actually merging with the sine x curve that is drawn over here like this, fine. And then if we just now take all of them together, and not only these many, but ideal and infinite number of terms together, then what we'll get is that we'll get the sine x completely represented by this infinite series. So there's an infinite series has to be really infinite in order to represent a particular function, correct? So that is why if we have only the series which we have for f in our case, we just have the series and its recurrence relationship. We really do not know the functional form of the f. How does the function look like? Here we have the series and as well as we have the function, and we know the function looks like this. We do not have the functional form from f. So what we can do is that in order to check how the functional form of that particular series that we have got for f behaves, we need to check how the coefficients for a large index, correct? So we see that this, as it is going to a 3 to 5 to 7, 9, and 11. Slowly, the function is those powers, the x to the 5 and x to the power 7, 11, 13, etc. They are actually going with the function. So it is necessary that we have to check the very high index coefficients, how those high index coefficient, where the index is very high, how those indexes are behaving to check the behavior of the series, right? That is exactly we'll be doing for our case. So now let's try to find out the behavior of the coefficients of f when I is pretty large. So we already have seen from our recurrence relationship that the ratio of a plus ai by 2 over ai is given by ai plus 2 over ai is negative of epsilon minus 1 minus 2i over I plus 1 I plus 2, and this ratio is going to be behaving like 2i over I square. That's because when I is very large, we can ignore epsilon, which is a small number. We can ignore 1 as well. And here also we can ignore 1 and 2 because I is pretty large. So therefore this denominator is, oh, this is going to be I square, not I. So let it be square, yes. So it's 2i over I square, which can be further simplified as 2 over I. So this ratio ai plus 2 over ai behaves like 2 over I when I is large. Now we have to check another series for which both the functional form and the series are known, and we'll see how that particular series behaves, particularly the ratio of two consecutive coefficients for large index number I behaves for that particular series that we'll check next. So let us talk about this series exponential q square given by this infinite Taylor series expansion where the ith term is this and the I plus 2 term is this. So therefore 1 over this I by 2 factorial is our AI and 1 over I plus 2 plus 1 factorial is our AI plus 2. Now, if we take the ratio of AI plus 2 to AI, just like that, we have done this for F, we get here that AI plus 2 over AI is going to be equal to 1 over I plus 2 plus 1 factorial and 1 over I plus 2 factorial, which I can write it down as I plus 2 factorial on top and then I plus 2 plus 1 factorial in the bottom, and this is simply I plus 2 factorial where I plus 2 factorial and I plus 2 plus 1, and this is equal to 1 over I plus 2 plus 1, which in the case of I is very large, where this 1 can be ignored. This becomes or equal to 2 over I for very so let me see, this one for very large I. So what we see is that the behavior of AI plus 2 over AI is exactly the same 2 over I when I is large for both the series of exponential q square and our f. What does this mean? It simply means that if both of these series, this e to the power q square, I know that if you just take the first term or the first two terms, it is not e to the power q square. But if we take many terms, infinite number of terms, then this series is going to be representing this function. We know this by now, correct? For sine x, the same thing happened. Now, if we have this series of f, and if f as also having infinite number of series in that, then f will also start behaving exactly the same way as this particular function e to the power q square. And therefore, in that particular case, if we really have the infinite series plugged into the solution, our solution was q psi of q, amplitude a, f of q, and then the asymptotic part was minus q square over 2. Now, if this particular function, which is represented by this infinite power series, is really, we keep the infinite number of turns, this particular series will start behaving in the same way as the function exponential q square, because that is exactly we have seen that this exponential q square, right, it has exactly the same ratio of ai plus 2 to ai for large I as the f, right? So if we really have an infinite series plugged in here into the solution, then this particular function ultimately will behave like an exponential q square and an exponential minus q square over 2, which is a exponential q square over 2. And this particular function will blow up, or it will just go to infinity when q will go to plus or minus infinity. So the purpose for which we introduce this asymptotic form, that the function should slowly go to 0 as q goes to plus or minus infinity, is this particular purpose of the second asymptotic form is defeated if we have this particular f as a power series solution, and if we really retain the entire series, that means all the terms of this series. And in that particular case, if you just really have all the series, then this function is going to behave like this particular function because their behavior is same, and therefore as a whole the solution will blow up for q equal to plus or minus infinity, and that is absolutely unacceptable. Clearly something is wrong. Now the question is, what is wrong? It seems that we have done everything correctly as far as mathematics is concerned. We have solved everything correctly. We have taken the correct boundary conditions that when q goes to plus and minus infinity, the whole wave function should slowly go to 0. Everything follows the rules and laws of quantum mechanics. So what went wrong? The only thing that is possibly wrong is our assumption that this particular f, the function which is represented by this series, is an infinite series. It is possibly not an infinite series. It is the same series where the coefficients are given by the recurrence relationship we have got, but just that this is not an infinite series. Maybe this particular function is represented by a series which has only few terms. It is getting truncated after only few terms. Now let's see under what condition this function f or the corresponding series for this f can get truncated after few terms only. So let us visit the recurrence relation once again. So we had got ai plus 2 and ai related by this factor. And if we just try to write down the series, the infinite series, in terms of now a0, a1, and other coefficients, what is obtained is that you have one infinite series with a0 and another infinite series with a1. So we have two independent infinite series going on, which is combinedly is giving this f, correct? Now the question is, this particular infinite series or this combination of two infinite series, this particular fq is going to be truncated after few terms only if the following conditions are applied. The first condition is that both a0 and a1 cannot be non-zero simultaneously. So either a0 is 0 when a1 is non-zero, or a1 is 0 when a0 is non-zero. What does it mean? It simply means that out of these two infinite series, only one will survive and the other will not. And the second condition is epsilon, which we have already seen to be just a number, is restricted to few values only. It can take only integer values, first of all, and that too, it can take odd integral values when a0 is 0, and it can take 0 and even integer values when a1 is 0. Now let us see with these two conditions how f is truncated. The first thing that I have done is that I have just rewritten this the factor in this way, where I have taken this 2i plus 1 within the parenthesis, and clearly as I is an index, so I can take only integer values, and when epsilon will take the value 2n plus 1 and n is any of the integers, we can clearly see that this particular factor is going to be 0 when I will become equal to n. So let's take one example to check what is happening. Suppose n is 3. So we get n is equal to 3. That makes my epsilon is equal to 2 multiplied by 3 plus 1 Hence, if I just try to take the factor for um, A3, for example, then what happens? This is equal to, this numerator is just going to be 2 multiplied by 3 plus 1 minus 2 multiplied by 3 plus 1 by 3 plus 1, 3 plus 2, and A3. Clearly, this is equal to 0, right? So that does it mean that now A3 multiplied by this whole thing was actually A5. So it simply means that when n is equal to 3 and hence epsilon is equal to 2 multiplied by 3 plus 1 coming from 2n plus 1, then A5 is 0, right? So therefore I get A5 is equal to 0 multiplied by A3 and hence A5 is 0. Now if A5 is 0, that will directly give me A7 is 0, A9 is 0, and so on and so forth. So therefore, in that particular series of f, as n equals 3, we already have the fact that a0 is 0, because when n equals 3, then a0 is 0. So therefore, in f, the a1 series is, the a0 series is not there already. In the odd series, I have got a3, but a5 onwards, all the coefficients are 0. Hence, in that particular f, we have only up to a3, or we have up to q to the power 3, q cube. That's the highest power in that particular series. So now when n equals 3, we get f to be not an infinite series, but rather a polynomial of degree 3. In general, what happens? That if we have n equals 3, then f of q is a polynomial of degree 3. In general, f of q is a polynomial of degree n, whatever n it is, 3, 5, 7, 7, etc. And that is how it works. Here we can ask a philosophical question. The question is that these conditions that we have imposed in order to truncate f, how justified are these? Why should we assume that these conditions are true? Well, we'll not assume that these conditions are true. What we'll do is that we have mathematically first found that if these two conditions are valid simultaneously, then f becomes not an infinite series, but rather f becomes a polynomial of certain degree. Now, these conditions that we have imposed, that will give us certain outcomes, it will have certain repercussions for this particular two conditions. And if those effects of the conditions are found to be true experimentally, then we'll assume that maybe these are true. Now the question is that if these two conditions are true, what is the effect that we see experimentally, what we should observe? Let's see that. So we have got epsilon is equal to 2n plus 1, where it can take values like 0, 1, 2, 3, etc. So as epsilon is now depends on some index n, let me call this epsilon as some epsilon n. Now we have defined epsilon previously as the ratio of beta over alpha. I can write it down one more time. So this becomes 2m e over h cross square, that is beta, and then we have H cross over M omega, that is 1 over alpha. So therefore this is basically epsilon. And now here we have the mass of the oscillator being M fixed. It has certain frequency of oscillation. H bar is a constant. So it simply means that if you have a different values of epsilon given by different values of n, this energy will change. It simply means that an oscillator of mass m having frequency omega can only have certain allowed energy levels indexed by n. And therefore, I'm now indexing the E also by the same index n, and I write it down like epsilon n. I can rewrite, so therefore this is equal to 2n plus 1, that's already we have seen this, and I can rewrite this again as 2m e n, and we have h cross square over here, that's fine. I'm just going to write this omega as 2 pi m nu. Now nu is the linear frequency of oscillation, and the right hand side remains as 2n plus 1. If we just rewrite, this will give me En to be equal to n plus half into h nu. So it simply means that we have got certain discrete energy levels for the oscillator, that is coming this particular discreteness of energy levels, the fact that the energies cannot just take any value is directly coming from the condition that we had imposed previously on epsilon, that epsilon can only take certain integral values, and that too in this particular fashion, 2n plus 1. The question is that as this particular restriction is directly related to these discreteness of energy, then the best way to check whether those restrictions that you had put, which made the series F truncated at the order n, whether those are true or not, that if we can experimentally check if these energy levels are true or not. And if we find experimentally that a particular oscillator of mass m and frequency nu are having exactly these energy levels, then we conclude that our restriction imposed on epsilon is true. So we finally get the very important result, the energy spectrum of a quantum simple harmonic oscillator. Here the lowest energy, which is given by n equals 0, the a is 0, which is given by half h nu, is also called the 0 point energy. Now let us see how the wave functions would look like. So we have understood by now that the wave functions will have a general structure which is going to be given by this form having some amplitude a. Then we should have an fq, which is turned out to be a polynomial multiplied by the asymptotic form, which is q square over 2. So the general form of the eigenfunctions are going to be something like this. Now we know that this f is now indexed by n, so I can write down n here, that is fn, and hence it is going to be psi n here, and this particular wave function will have an energy eigenvalue which is En, and En has already been discussed over here. So this En, now given a particular value of n, we can calculate from the frequency of oscillation what's the actual value of energy. Now that's the eigenvalue, and the corresponding eigenfunction is this. So let's have a look of first few eigenfunctions, how these Fn, this polynomial, does look like, and then we can draw them, the first few of them, to have a feel of how the wave functions are, how the wave functions look like for a simple harmonic oscillator. So I have written down the first few wave functions for n equals 0, 1, and 2. I call them psi 0, psi 1, and psi 2. All of them are actually a function of q. And I have used a different normalization constant a0, a1, and a2 for them. And later we'll see what a0, a1, and a2 should look like. But first we will check what the functional form that we get. So the first thing that we see is that the asymptotic part is there for each and every wave function. That's constant. That's fine. What is changing is the form of f. Here, the f is basically 1. There is nothing. And here, the f is just represented by q. And here, f is 1 minus 2q squared. As I have already told, that for a particular n, f is just a polynomial of degree n. So here, as n is 0, so the f should be a polynomial of degree 0, which is basically a constant factor, a constant. So we can call it a0, for example. Now the a0, which is over here, is absorbed in this particular constant. There is no point in keeping two different constants. We can simply multiply them, and then we can bring a new constant. And that is our a0. For n equals 1, f is a polynomial of degree 1. Degree 1 means it's q to the power 1, just q. So we have a q here. The corresponding coefficient was probably a1, and now that a1 is absorbed in this capital A1. For n equals 2, f is a polynomial of degree 2. That means the highest power of q is q square, and this is the form. We'll be discussing shortly that why this particular form is coming, but nonetheless we can clearly see that this is a polynomial of degree 2, and we should have a0 outside as a common constant, like here, like a0 over here, because of the q square. This factor a2 over a0 is coming to be 2 here. I'll be discussing why this particular thing is coming to be 2. But nonetheless, this a0 should be here, and that a0 is now again absorbed in this big normalizing constant a2, and there's no point in keeping two different constants. So either the a0 or a1, depending upon which one is non-zero, are always absorbed in this normalization constant, and we'll be normalizing these wave functions later. Now let's see how they look like. So here this energy En, as we have already found. So now if we just check the n equals 0 level, so the energy is just going to be half h nu, and that is exactly what it is being plotted here. The energy level is, so this 0, 1, 2 are in units of h nu. Now the E0 is basically half h nu, that is exactly in the middle here, half h nu, and the function is just an exponential decay, and this exponential decay is this e to the power minus q square by 2 function. So it is at x equals 0 or q equals 0. So let's try to write down this is a q equals 0, and this is our q line instead of x. It doesn't matter. I have taken this particular nice picture from Wikipedia, where the variable is used as x. We are using the variable q. Really doesn't matter. So half h nu is the energy, and the wave function, it is symmetric about q equals 0. It is just as it is minus q square over 2, so it is just simply decaying as a q square. That is how this particular thing was. What's the second one? Second one should be E1, then it is a 1 plus half, so it's basically 3 over 2 h nu, and that is exactly where this has been placed, 1.5. That is the energy level, right? And as this is the energy level, so uh, this line is showing the classical limit, because the wave, the potential is more than this energy beyond this point. So a classical oscillator will be bound between this region, right? So these lines, these dotted vertical lines, are basically showing the classical limit of the oscillator. Although quantum mechanically, we know that as this potential is not exactly infinite at this particular point, but this is going to be infinite when q is going to be plus infinity or minus infinity. So there will be, the wave function will go slightly into the classically forbidden zone, and then it will go to smoothly to 0 because of this e to the power minus q square factor. Nonetheless, so we see that we have a situation that we have some function over here which goes slowly there. So what is happening? We have q, right? This is the thing. So if we just try to plot it, right? If we just try to plot it, so this is going to be the axis, and now I can see that this is my q. So it is a q versus the function fq, right? So this is a straight line, a q is there, but as it is going plus and minus q, q goes plus and minus infinity, that means it is going far away from this side or far away that side. This exponential factor, the asymptotic part, will take over this polynomial, and then what will happen is that after some time this will start going down, and this is also happening this side, it will start going down to 0, and that is exactly what we get here. So it is started, this middle portion is basically the 45-degree line given by this q versus q, y equals x. This is a 45-degree line, and then after some time this asymptotic part, e to the power minus q square by 2, takes over and brings it down slowly to 0 when q is very large, both sides. And then each and everything, if you can go out, so basically all you have to do is that you have to first plot the polynomial and this end part of the polynomial when the q or x is reaching towards the classical forbidden classical limit. Then this particular asymptotic part will slowly bring this wave functions down to 0, no matter what n is, n1, 2, 3, 4, etc. And the corresponding energies are just going to be like this: half or 3 by 2 or 5 by 2 or 7 by 2 or 9 by 2 h nu, and these are the wave functions, and that is how the simple harmonic oscillator works. Let us quickly check why certain f has that a particular form. For example, I have taken here the case of f2, that is there in n and psi 2, right? So this is our f2. Now f2 has this particular form, and the general form for f is this. So when n equals 2, we know that a1 has to be 0, right? So let's first remove a1 just to keep this a0, and also as it is just f2, so we really do not have anything starting from here, so we have simply starting the or this, the whole thing is ending at q to the power q square. So let's remove this part as well, and just remove this enter A1 part, right? Okay, so I have removed the terms in the A0 series beyond Q square, and also I have removed the entire A1 series. Here we should uh, see that n is equal to 2, correct? So hence here epsilon is given by 2n plus 1, and hence it is 5. Now let's try to find out the ratio A2 over A0 from all these things, right? So we can get a negative sign, and epsilon is 5. So we get 5 minus 1 minus 0, because I equals 0, that is I2 by A2 by A0, so I equals 0. And then we get 1 multiplied by 2, because I equals 0, and that is equal to minus of 2, because it is 4 divided by 2, and it's minus 2. So we get this particular thing, that A2 over A0 is equal to minus 2, and that is exactly what has been plugged in here. So we have this 1 from here, that is the same 1, and then A2 over A0 is coming to be minus 2, so therefore it is 2, and then Q square. And if we just use this particular formula for a particular value of epsilon, a particular value of n, we can find out any ratio of ai plus 2 by ai, and you can keep on doing this series. This is very simple, and this a0, as I have already told, this a0 constant, this is not determined yet. This particular constant is going to be absorbed into this overall normalization constant, and we have to do the normalization as the next step. So let's go back to the normalization of each of these psi n, and let's see how to normalize them. So in a way, for a particular psi n, right, we have to find out the a n corresponding to that particular function. So for normalization, what we should get is that this integral from minus infinity to plus infinity, uh, psi star n q psi n q dq should be 1, right? And that directly gives me the fact that this is some a n square outside and goes to minus infinity to plus infinity, and this factor multiplied to itself will give e to the power minus q square. This by 2 will disappear, right? So I get exponential minus q square first, and then we get fn of q, and again fn of q, and then dq is equal to 1. Now these Fn, right? These are actually the Hermite polynomials. These polynomials are known as Hermite polynomials. I'll tell you shortly after this normalization thing is done that why are they called Hermite polynomials. Uh, but they have a particular property that we have to use here. So this is a particular property of Hermite polynomials, and that property is like this. So in principle, we can use this particular quantity for this entire integral, right? And if we do that, what we get is the following. So we get our coefficient an, the normalization coefficient an, to be this whole factor. We can write one or two terms like a0 and a1 if we wish. So this way we can write any term like a1, a2, a3, a4, a5, and then we can construct the whole wave function, which is a solution for quantum simple harmonic oscillator. This normalization constant is given by these factors. We have the asymptotic form, then we have the Hermite polynomials of degree n, depending upon which one we are trying to write. And that's pretty much is the wave function for a simple harmonic oscillator. Now, if we can quickly check why these the f or fn are called the nth order Hermite polynomials. That is because we have seen that this epsilon takes this value 2n plus 1, or another way, epsilon minus 1 is equals to n. And if this is true, then the original differential equation from which we obtained f as a series solution, that equation takes this form, where this epsilon minus 1 in the original equation is replaced by 2n because of this condition. And this differential equation is a very well-known, well-studied differential equation. And the solution to this differential equation are called the Hermite polynomials of degree n, depending on what n we choose in the equation. N can be 0, 1, 2, 3, 4, whatever integer values, depending upon that. So therefore, we get the solution to this particular equation, which we are calling Fn of Q, right, are directly related to the Hermite polynomials of the same order. And that is why we can use the properties of Hermite polynomials in any of the problems or any of the normalization constant finding thing. We'll be using this particular fact that these f's are actually Hermite polynomials. Later also, when we'll solve a couple of problems on simple harmonic oscillators. But before that, let's talk about one very interesting thing, that is the probability of finding a particle which is executing a one-dimensional simple harmonic oscillation, and compare that probability of finding a quantum particle with a classical counterpart which is also making a one-dimensional simple harmonic oscillation. So let's try to understand the difference and similarity between these two probability distributions, the probability of finding the particles, and that's one very important thing to know. So let us first talk about the classical probability distribution. Imagine you have a classical oscillator which is oscillating about this zero position, x equals 0, you can call the equilibrium position. It has certain amplitude, correct? So it is going back and forth. So now if we have to define the probability of finding this particular mass, right? Classically we define it that the position, right? A particular position, suppose you have any small amount of position, correct? We can call it a dx. Okay, the amount of time this object resides in that particular space dx, right? The probability of finding the particle there is directly proportional to that. So longer it stays here, the more probable that it will be found there, right? It simply means that if the particle, while moving back and forth, it is having a lower velocity at some point, it is more probable that the particle would be found there, because per unit time it is staying longer in that particular place, right? So we know that a classical oscillator, when it oscillates, it goes all the way to the end of its amplitude and it stops there momentarily, and then the entire energy there becomes potential energy, kinetic energy becomes 0, and then it starts its back journey all the way, and when it reaches its equilibrium position, its entire energy is kinetic energy. So therefore the velocity is maximum there, and then it goes the opposite direction and slowly slows down, and then it goes to the amplitude position again and it stops there and goes back, right? So therefore the velocity pattern has maximum, the velocity is maximum here and 0 at the two edges. And if the probability is directly proportional to, or not directly proportional, rather it is inversely proportional. More the velocity, less the probability, right? It's inversely proportional to the velocity. Then we can draw the probability distribution as a function of x as this. So we can write down the same x here, and we have this two edges. A classical particle does not go beyond this, so there is no probability of finding the particle in this region or in this region, because this is classically forbidden region. In a classically forbidden region, a classical oscillator will never go, and the velocity is maximum here, so the probability of finding particle here is minimum, and it goes up slowly as it reaches towards this edge, and as it stops there, v becomes exactly 0 at this particular position. And if it is inversely proportional to the v, then the probability at this particular position and at this particular position, the two ends of its journey, it becomes infinite. So the probability becomes this as a function of x. So it goes, it's a minimum here, and then it goes up, the probability, and then becomes infinity. It goes this way also, it becomes infinity. And then it suddenly drops to 0 because it's a classical particle and the probability is 0 at the outside. So this is the pattern we get when we have the classical particle making an SHO, simple harmonic oscillator. Now, if we have to do the same thing with a quantum particle, all we need to do is that we have to simply get the corresponding wave functions that you have obtained, the psi 0, psi 1, psi 2, etc., etc., and you have to take a mod square of them, and that will give us the probability density. We know that, right? So let's try to do that, and we'll try to find out what the the quantum probability distribution look like. So here is the quantum version of it. I have taken this picture again from Wikipedia. It's a nice picture where we have got the psi 0, psi 1, psi 2, and psi 3, and their corresponding squares, right? These are real functions, so it doesn't matter whether you are taking a mod square or direct squares. What we find is that at least look at the ground state, psi 0, where the probability distribution is of this form, right? So here the probability was minimum at the equilibrium position, which is x equals 0, and it was maximum towards the edges, whereas here the maximum probability is actually in the midpoint, x equals 0, and it is the lowest towards the classically forbidden region, and then it goes a little more beyond the classically forbidden region because it is it's a quantum particle. But what is important is that the feature is exactly opposite of that of the classical distribution, right? Now the question is, now if we just keep on increasing the n from 0 to 1 to 2 to 3, we see that slowly the distribution, the probability distribution, is taking a form that it has having a higher probability towards the edge, right? It is just the psi 3 squared, nothing else. This is the psi 3, you just square it and it is this. And this particular thing is having an idea that you have a picture like this in the classical forbidden zone like this, right? And this is a classical forbidden zone like this, right? And then the probability distribution is having a shape like this. This is exactly the shape that is that we got for the classical case. So what does it mean? That as we are increasing the quantum number n from 0, 1, 2, 3, 4, if we go to really, really high, it will actually mimic pretty much the classical picture, okay, of this particular thing. Let me give you another example for where the n is very high, and we'll then compare whether this classical picture and quantum picture is actually matching, which is according to Niels Bohr and its correspondence principle should be the case that when the quantum number n, here the quantum number is m, because that is the number which defines the wave function psi n, defines the corresponding energy En and everything. So when this quantum number n is very high, what happens is that this entire quantum world is started mimicking the classical world, and that it should be. So let me give you that particular picture for n when n is very high, and then we can check and we can see that how good it is matching. So here is the probability distribution for n equals 12 psi 12 mod square, and this black line shows exactly the probability distribution for a classical one. This dotted line is the probability distribution for a classical particle, which I have also tried to draw here, more or less. And then if you take the psi 12 mod square, it basically almost similarly mimics the classical distribution, that you have a nice distribution like this, which is supposed to be this, exactly this one. So as we are increasing n from 0 to all the way to 12, it has started mimicking the classical particle. And if we really go n tending to infinity, right, we can see that we can directly come back to the classical distribution. So that is the Niels Bohr's correspondence principle. It should be the case, and it is the case for simple harmonic oscillator. So let me conclude this part of the lecture 2 on the simple harmonic oscillators. This concludes the theoretical derivation of the entire quantum SHO. I might just prepare one more lecture, which is kind of a supplementary lecture, where we'll be discussing few problems, which are very common problems that we generally discuss on this topic. But as far as the derivation of the primary theory is concerned, that part is concluded here. So it's bye-bye from me now, and I'll see you in the next lecture with few more problems.